This is Christopher Powell, and I am following Jarvi Bihat and Miriam Yazdamvar. And for the presentation part number 2, I'm going to be discussing what is called the Bayesian Adaptive Goldilocks design, which is an alternative for the SHINE trials that they've been speaking to you about with regards to stroke victims and hyperglycemia after the stroke and these clinical trials. So the SHINE trials, they had to have an alternative design, and they chose this Bayesian Adaptive Goldilocks design, which is another form of responsive adaptive randomization. And in the literature, it showed that this design framework includes frequent interim looks in order to decide whether the trial should be stopped early due to successes or failures. And those frequent interim looks and subsequent stop or continue decisions are based on the predictive probabilities. And we all remember Bayesian statistics. So the nuts and bolts of this design, and this means that the Bayesian statistics, as we all recall, we have to view the posterior probabilities of the success rates between the two treatment arms and then compare them. And patients are assessed for their modified Rankin scale or MRS score at 6 weeks, so that a longitudinal model, like repeated measures, for example, of the main endpoint can be utilized to let the 6-week modified Rankin scale score aid in the prediction of what the MRS score will be at the end of 90 days, which is the end of the treatment goal. So with the Bayesian Goldilocks, the randomization scheme is as follows. The patients are equally randomized to either the control arm or the experimental arm. The minimum sample size is 500 patients, and the maximum sample size is 1,400 patients. And the way it works is that for every additional 100 patients enrolled after the minimum amount of 500, there are additional interim analyses scheduled. And the Bayesian Goldilocks alternative design uses a one-sided alternative hypothesis. And the one-sided alternative hypothesis is that the success rate on the experimental arm is greater than on the control arm. And why just use a one-sided alternative hypothesis here? Well, the clinical outcomes of reaching no difference between treatment and control arms, which is known as futility, and the experimental therapy being worse than the control, are the same. Is Bayesian Goldilocks an ethically sound alternative study design? As with previous responsive adaptive randomization schemes, there's been some questions about ethics raised, and so I tried to look to see what I thought about the study design. So if either of the previous two clinical outcomes from the previous slide are evenly matched, in other words, there is no difference between treatment or control, or the experimental arm ends up being worse than the control arm, then patients would just continue receiving the control treatment. And the control treatment is the current standard of care, which means that the Bayesian Adaptive Goldilocks alternative design would not continue to just show the experimental therapy is significantly worse than the control. So therefore, in my opinion, it is an ethically sound alternative design. Nobody is being harmed. And as I discussed before, one of the main features of the Goldilocks design is more interim monitoring. And as explained during randomization, after the 500 patients are enrolled, the minimum sample, every additional 100 patients adds one interim analysis. And since there are a maximum sample size of 1,400 patients, that gives a maximum of 9 possible interim analyses. So at any interim analysis, if the probability maximum is less than 5%, the trial will be stopped due to futility. In the opposite regard, at any interim analysis, the trial will be stopped due to success if the probability of the sample is greater than 99%. So therefore, the trial is stopped based on either of the following values being obtained in an interim analysis: P max greater than 5% and P sample less than 99%. And after we go through the interim monitoring, get to what's called the primary efficacy analysis. And whether the accrual stops early or continues to maximum sample size, the primary efficacy analysis will be conducted at the 90-day follow-up. And the probability of success is theta j, and it is assumed that this probability of success has a beta prior distribution, theta j approximately equal to beta x1 or y1, where j is equal to c, which is the control arm, and j equal to e is the experimental arm. At each interim analysis and at the final analysis, the number of observed successes, xj, among the currently enrolled patients, nj, is modeled as a binomial distribution. So we see here xj approximately equal to binomial distribution of nj comma theta j. And so the prior distribution is updated with the currently observed data, xj and nj, and the resulting posterior distribution is theta j with xj comma nj approximately equal to beta 1 plus xj comma 1 plus nj minus xj. And given the amount of successes in each group, which is control group xc and experimental group xe, and the total amount randomized to each group, which is nc and ne for the experimental group, the primary analysis is the probability of theta experimental being greater than theta control with the trial data equal to the double integral and gamma and 2 plus the sample of the experimental over gamma of 1 plus xe experimental group times gamma parentheses 1 plus sample of experimental minus x experimental actual times theta raised to the exponent of x e experimental to the subscript of experimental times 1 minus theta to experimental in parentheses times or raised to, n to the experimental minus x to the experimental, and that's times gamma times 2 plus nc in parentheses over gamma 1 plus xc times gamma 1 plus nc minus xc in parentheses times theta raised to xc with subscript c times 1 minus theta c in parentheses raised to nc minus xc, and then times the derivative of theta c times the derivative of theta e. Okay. So the value is compared to 0.0979 in the final analysis. If the posterior probability that the success rate on the control arm theta c is greater than 0.979, the treatment will be considered a success. So the probability of theta experimental greater than theta control next to the trial data greater than 0.979. And the probability of 0.979 is like having a one-sided critical value of 0.021 in a frequentist trial. And this critical value was selected via simulation to help control the one-sided type 1 error rate of the trial to less than 0.025. And that's equivalent to SHINE's two-sided 0.05 type 1 error rate. And longitudinal model and predictive probabilities to make use of the predictive probability calculations, the information from patients with incomplete information to the extent that the baseline and 6-week assessments are associated with the primary endpoint at 90 days. The patients with complete information inform this association. And a Bayesian model is designed to learn from the associations between the earlier 6-week time point and the primary 90-day endpoint. Each arm uses 3 beta binomial distributions to model that transition. And the Bayesian Goldilocks construct for both the control arm and the experimental arm, the 3 beta binomial distributions are: number 1, from baseline to 90 days for patients with baseline information only. Number 2, from 6 weeks to 90 days for patients who were a success at the 6-week mark. And number 3, from 6 weeks to 90 days for patients who were not a success at 6 weeks. And we have here a comparison table with the SHINE versus the Goldilocks results. And in regards to hypothesis testing, SHINE is two-sided, Goldilocks, like I said, is one-sided. The primary analysis for SHINE is covariate adjusted, whereas Goldilocks is unadjusted. The randomization for SHINE is responsive adaptive, whereas Goldilocks is 1-to-1. And the minimum sample size for SHINE was 600, and Goldilocks was fixed at 500. Maximum sample size for SHINE was between 1400 and 1718, while Goldilocks was fixed at a maximum of 1400. The planned interim analyses were 4 for SHINE, but 9 for Goldilocks. Stopping boundaries were grouped sequential for SHINE, and stopping boundaries were predictive probabilities incorporating early information for Goldilocks. And the complete follow-up of all patients in event of early termination in the SHINE trial was defined by the undefined critical value, and in Goldilocks by the explicitly defined critical value. And you can see here a side-by-side plot. On the left plot is the mean of total sample size, with X being the Goldilocks plot and the circle representing the shine plot. And the heavy line represents a control success rate of 25%. The medium line represents a control success rate of 30%, and the light line represents a control rate of 35%. The dashed line on the right panel shows 80% power for reference at the top there. So basically you can see for the treatment effect on the left side with regards to mean of total sample size, you can see that the Goldilocks has a much smaller sample size curve, and the success rates are very tightly wound together for the Goldilocks experiment treatment effect. The SHINE trial has the heavy lines very segregated from the other two lines with the circles for the sample size. So there's much greater variability in the sample size and a much larger sample size in the SHINE group versus the Goldilocks group. And on the right plot, we see the probability of success plotted against the treatment effect. And we can see here the circle is the SHINE and the X is the Goldilocks alternative. And you can see, other than the starting point, they pretty much almost mirror each other towards past the power mark of 80%. So in a summary of SHINE versus Goldilocks, the Bayesian Goldilocks design strengths are: number one, more frequent interim analyses; number two, the longitudinal model of the primary outcome; number three, exclusive accounting for patients with incomplete follow-up if accrual to the trial was to stop early; number four, sample size advantages, which is an increased potential to stop the trial earlier, which would allow patients outside the trial to be treated with a better therapy faster. Goldilocks weaknesses and fate. Ultimately, the researchers chose not to implement the Goldilocks design. They only ran simulation studies with the Goldilocks design. Despite the similar error rates, the differences in sample size and power of the two designs are confounded due to the difference in hypothesis testing, where the standard of care arm is just slightly better than the tight control arm. And if you remember back to the Goldilocks design, it is only a one-sided alternative hypothesis, and two-sided trials are usually considered the standard. So final thoughts on Goldilocks design. I use quotes because they said it best, the authors. The Goldilocks design stops accrual for predictive success if the probability for success with the currently enrolled patients, allowing for the outstanding approximately 100 patients to reach their 90-day endpoint, is greater than 99%. There is a small chance that the trial could stop for predicted success, complete follow-up of the enrolled patients, and then at the final analysis miss the 0.979 posterior probability threshold required for trial success. Therefore, the researchers knew that a data and safety board monitoring board, DSMB, wouldn't likely let the Goldilocks trial to proceed, just to show that an expensive, more laborious therapy is in fact significantly inferior to the standard of care. So, thank you for watching, and take care.